Assalamu alaikum. Good morning. It's a pleasure to be here today to give my lecture. My name is Mohamed Khayet. I'm professor at the Faculty of Physical Science of the University Complutense of Madrid. And also I am associate researcher in Madrid Institute for Advanced Studies of Water and chair of the research group Membranes and Renewable Energy. Today, my lecture, I divide it into three parts. First of all, I would like to give general and brief description of membrane distillation technology. Then the characteristics required for a membrane to be used in membrane distillation. And finally, I will share with you some case studies on surface modified membranes for MD, flat sheet, hollow fiber, micro and nanofibrous membranes. Membrane distillation is non-isothermal separation process used generally for desalination. The membranes to be used in membrane distillation must be porous and hydrophobic. And the driving force here is the temperature difference, which induces the vapor pressure difference between both sides of the membrane. Because of the hydrophobic character of the membrane, there is formation of liquid vapor interfaces at both sides of the membrane pores. So in this case, the temperature, for example, here is higher than the other side of the membrane. The vapor pressure here is higher than the other side. So there is the water molecules that evaporates from this hot liquid liquid vapor interface, cross the pore in vapor phase, and then condense on the other side of the membrane. We have here four main MD configurations in order to establish this driving force: direct contact membrane distillation, sweeping gas membrane distillation, air gap membrane distillation, and vacuum membrane distillation. MD has various advantages, and I would like to mention here some of them. The first one is the high separation factors achieved, which is higher than 99.9% whenever you use non-volatile solutes in the feed solution. You can produce not only distilled water, but also ultra-pure water. Also, MD can be used for the treatment of high salinity solutions up to saturation. In this case, you can, for example, treat reverse osmosis brine and look to zero liquid discharge, for example. If you have a look to this figure, you can see the tremendous increase of the number of papers published each year up to December of last year. We have published 2,455 papers. Like any other membrane separation process, MD has also some drawbacks, such as the membrane pore wetting, the internal heat loss, which is associated to heat transfer by conduction through the membrane matrix, the vapor pressure polarization, which is associated to the temperature and concentration polarization effect, and also the uncertain long-term operation associated to membrane pore wetting, especially in those semi-pilot plants that use commercial membranes prepared for other purposes rather than for MD. The big problem here is the no availability of membranes designed specifically for membrane distillation. This is why various research groups start to work on MD membrane engineering during the last decades. If we have a look to this figure, we can see the increase in number of published papers each year up to December of last year on fabrication and modification of membranes for MD. Up to December of last year, we have published 703 papers, which is 28.6% of the total number of published papers on MD membrane preparation. What are the characteristics required for membrane to be used in membrane distillation? Other than the porous structure, the good thermal stability, excellent chemical resistance, the high permeability, two other main characteristics are important here for an MD membrane. The first one is the high liquid interpressure of water that must be achieved using membranes with high hydrophobic character and small maximum pore size. And the second one is the low thermal conductivity, which can be achieved using membrane with high porosity or high body volume fraction. During the last 15 years, we worked on MD membrane engineering. And here I would like to share with you some cases on composite porous membranes, hydrophobic, hydrophilic double layered in flat sheet and hollow fiber forms, and also nano-fibrous membranes. Flat sheet and hollow fiber membranes. The idea here is to design porous composite hydrophobic hydrophilic membranes for the configurations, direct contact membrane distillation, and liquid gap membrane distillation. In this case, the liquid permeate is brought into contact with the hydrophilic layer of the membrane, which has bigger pores. So the liquid penetrates inside the big pores of this hydrophilic layer. So we can reduce here the distance between liquid vapor interfaces. Whenever you reduce this distance between the liquid vapor interfaces, you expect to increase the permeate flux, and also at the same time, you can reduce the heat transfer by conduction if you design well this hydrophilic layer. How we prepare these membranes? We prepare them in simple step by phase inversion technique. First of all, we dissolve the polymer solution. We use a host hydrophilic polymer. We dissolve it in solvent. We add an additive for pore formation, and we add also fluorinated polyurethane additive. We cast the membrane. We expose it to solvent evaporation. During solvent evaporation, this FPA migrates to the surface of the polymer air interface, changing its characteristics because of its lower surface free energy compared to that of the host hydrophilic polymer. Then we coagulate the membrane, we immerse it in ethanol water solution, and in order to preserve the formation of the pores, and finally we dry it in air at ambient temperature. These FPA are synthesized in two steps polymerization. First of all, we mix the isocyanate with polyol to get an urethane prepolymer. This urethane prepolymer is end capped with fluoroalcohol to get the fluorinated polyurethane additive, which consists of mean polyurethane chain terminated with two fluorine segments. We prepare different types of PAs, and we are interested in those FPAs that exhibit high fluorine content and low molecular weight in order to favor the migration of this FPI towards the polymer air interface. We developed various research studies on FPI modified flat sheet membranes. And here just I would like to share with you a case study on the effect of the host polymer concentration. In this case, we used as host hydrophilic polymer polyethyramide. The concentration of PI was maintained at 2 weight%. The concentration of the host hydrophilic polymer was varied from 10 to 20 weight%. And you can observe that the water contact angle of the modified membranes is higher than that of the unmodified membranes. This is a cross-section of the modified membrane, and these are the AFM images of the top surface and bottom surface of these modified membranes. We confirmed the migration of this FPI by Spmdx analysis. We focus more on the concentration of fluorine because fluorine is associated to FPI. And we observed that the concentration of fluorine is higher at the top surface compared to that when we go down inside the membrane. We used also X-ray photoelectron spectroscopy analysis carried out at different takeoff angles in order to study the migration of this FPI to the polymer air interface. And we observed also that the concentration of fluorine near the top surface is higher than that far from the surface. So this confirms also the migration of PI to the polymer air interface. We characterize these membranes by different techniques. For example, liquid interpressure of water, pore size, effective porosity that takes into consideration the tortuosity of the membrane pores. We observed that the liquid interpressure of water of the modified membranes is higher than 3 bar, but the pore size is below 25 nanometers. And this is an order of magnitude smaller than the pore size of the commercial membrane. So, but surprisingly, when we use these membranes in direct contact membrane distillation or desalination, We observe that the permeate flux of these modified membranes is higher than that of the commercial membranes prepared for other purposes, as said before, for microfiltration purposes. And the reasons behind this is, as I said before, we could reduce the distance between the liquid vapor interfaces formed at both sides of the thin hydrophobic layer. The other reason here is the mechanism of mass transfer. For the modified membranes, the pore size is very low, below the mean free path of the evaporated molecules, so Knudsen type of flow is applied. However, for the commercial membranes, the combined Knudsen and Brownian molecular diffusion is the mechanism of transport for these membranes. Finally, we use these membranes for long-term operation, more than 3 months in desalination using saline solutions up to 200 grams per liter. The modified membranes, they work very well with very high salt rejection factors. However, the commercial membranes, they got wet just only after some days of operations. Therefore, we propose the modified membranes for the treatment of brine or petrol industrial wastewater. Let's move now to the modified hollow fiber membranes. The situation here is very challenging because this FPI can migrate towards the inner surface, the outer surface, or both the inner and outer surface. Dry wet spinning technique is normally the method used to prepare the hollow fibers. As you can see here, we have a lot of parameters associated at the same time. So if you want to study migration of FPI towards the inner surface or outer surface, is very challenging, more than that for flat sheet membranes. We carried out the various research study on FPI modified hollow fiber membranes, and just only I would like to share with you a case study here on the effect of the host polymer concentration. As host hydrophilic polymer, we used polyethylamide. Its concentration was varied from 14 to 17%. The concentration of FPI was maintained constant at 2%. It is important here to measure the surface tension, the viscosity of the polymer solution, because they affected the diameters of the prepared hollow fibers. All other spinning parameters were maintained the same, and we observed reduction of the outer diameter of the hollow fiber upon the addition of FPI in the polymer solution, and also with the increase of the concentration of the host hydrophilic polymer. This affects also the thickness. These are some SEM images of the cross-section of the hollow fibers. And in terms of FPI migrations, we measured first the water contact angles of the outer and inner surface of the hollow fibers, and we observed an increase in water contact angle for the modified hollow fibers. You can observe here that the outer layer is more hydrophobic than the inner layer. We confirmed this result by Spmdx analysis. We focused more on the concentration of fluorine. As I said before, fluorine is associated to FPI, not to the host hydrophilic polymer. And we observed higher concentration of fluorine at the outer surface than at the inner surface, whereas the concentration of fluorine in the center were the lowest. This indicates that effectively there is migration of FPA from the center to the outer surface, whereas that of the inner surface was maintained constant. This is attributed mainly to the fact that it is more likely that coagulation of the hollow fiber starts from the inner surface. So there is not much time for FPI to migrate to the inner surface. Finally, we confirmed also this result by XPS analysis, and we observed that the concentration of fluorine is higher at the outer surface than at the inner surface. So the outer surface is more hydrophobic than the inner layer. We characterize these membranes by liquid interpressure of water, and we observed higher liquid interpressure of water values for the modified hollow fibers, as you can see here, higher than 3 bar. The pore size, effective porosity, and porosity were reduced with the addition of PI. And the mechanical properties were also improved: young modulus, tensile strength, and elongation at bricks whenever we added FPI to the polymer solution, similar to what occurred for flat sheet membranes. Finally, we use these membranes in desalination by direct contact membrane distillation, and we observed higher permeate flux for the hollow fibers prepared with the lowest concentration of the host hydrophilic polymer. So we selected finally this hollow fiber for further experiments, and we observed quite stable permeate flux with quite stable electrical conductivity of the permeate below 6 microsiemens per centimeter. So these membranes are very robust with high liquid interpressure of water for desalination by DCMB. Let's move now to nanofibrous membranes. In 2008, we proposed for the first time the use of nanofibrous membranes for MD technology because of their high permeability, low thermal conductivity, high porosity or void volume fraction, other than other suitable parameters for an MD membrane. And these membranes are prepared normally by electrospinning technique. If we have looked to this figure showing the increase in number of papers published each year since 2008, up to December of last year, we have published 145 papers on electrospun nanofibrous membranes for MD, which is about 20.6% of the total number of published papers on membrane fabrication and modification. Electrospinning is not an easy technique to prepare nanofibrous membranes because we have to apply high electric voltage up to 30 kilovolt. We have to establish an electric field between the metallic needle and the collector. So we have here a lot of instabilities. And if we want to study migration of PI towards the surface of nanofiber, it is not very easy. It is more challenging than for hollow fibers because we have a lot of forces applied at the same time. I just would like to share with you a case study here on PI concentration. As host hydrophilic polymer, we use polysulfone, and the concentration of PI was varied from 0 to 6%. All the electrospinning parameters were maintained the same. It is important here for electrospinning technique to know the electrical conductivity, surface tension, and viscosity of the polymer solution. These are some SEM and TEM images of the nanofibrous membranes. You can see that we could prepare bit-free nano networks, and with the increase of the concentration of FPI, the nanofibers acquired more curved nanofiber structure, as you can see here, with larger size, wider size distribution, rougher, and even corrugated. The corrugations are aligned in the direction of the nanofibers. Below here, you can see the TEM images of the polysulfone nanofiber, which is uniform and homogeneous, and those of the modified nanofibers, which show more heterogeneous structure. We characterize this membrane by X-ray photoelectron spectroscopy analysis carried out at different takeoff angles, as you can see here. And we observed that the concentration of fluorine in the nanofibers increases with the increase of the concentration of FPI. And this is normal. The important result here is the reduction of the concentration of fluorine with the increase of the angle attack. And this confirms the migration of PI towards the surface of the nanofiber or microfiber. This result was also confirmed by the measurement of water contact angles, and we observed an increase in water contact angle with the increase of the concentration of PI, even we could prepare super hydrophobic nanofibers. The mechanical properties were also improved as we observed for flat sheet and hollow fibers. The thickness also, you can see here that it is increasing with the increase of the concentration of PI, and this is attributed to the increase of the nanofiber diameter. It was not expected the increase of the void volume fraction with the concentration of PI because the conductivity was increased, and this result associated mainly to the increased thickness and the nanofiber diameter. We also measured the interfiber space, minimum, maximum, and mean. These are the results. And let's move. No, I want the previous slides. Just 1 second, please. This one. Yes. And we can see here the liquid interpressure of water, the increase of the liquid interpressure of water with the increase of the concentration, the reduction of the liquid interpressure of water with the increase of the concentration of PI. And this is associated mainly to the increase of the maximum interfiber space rather than the superhydrophobic character of the membrane. If we focus more on the values of the liquid interpressure of water of the nanofibers membranes prepared without FPI and with the highest concentration of PI, we can observe the lowest liquid interpressure of water. And this is why when we use these membranes for direct contact membrane distillation, they got wet just only after some times of operation. However, the other three membranes, they worked very well without any problem. And with an electrical conductivity of the permeate below 8 microsiemens per centimeter. Based on the obtained permeate flux, we selected these two membranes for further experiments, and we observed quite stable permeate flux with quite stable electrical conductivity. The permeate flux were competitive to other designed superhydrophobic nanofibers membranes. So finally, just only to sum up, I would like to say that FPI do migrate to the surface of flat sheet, hollow fiber, and nanofiber or microfiber surfaces, rendering them more hydrophobic with higher liquid interpressure of water, robust for long-term operation of desalination by direct contact membrane distillation. And finally, just I would like to acknowledge the funds from the European Union and Spanish ministries, the members of my research group, and also other researchers from other institutions. This is my emails. And if you are interested in membrane science and technology, you can recommend you these 4 books on membrane distillation, membrane modification, evaporation, vapor permeation, and membrane distillation, and osmosis engineering. And thank you so much for your attention.